Alright, I'm sorry guys for the last video. It was eternal. I'm gonna cut through all the the intermediate steps. You get the idea how I got the damping ratio, so I'm just gonna go ahead and tell you what the natural frequency is with the simplifications we made in terms of rocket parameters. Okay, so you can see that the natural frequency is going to be the square root of dynamic pressure, the reference area, phi prime over moment of inertia. If you substitute this, remember I defined. Well, I gave you the simplification on the previous video for the moment of inertia for phi. Little change I'm going to do is that for phi, so this is something I didn't do in the previous video, but I think it's going to simplify things a bit. For phi prime, well, you had different you had different CN alpha fin for Mach below Mach linear and Mach above Mach linear, so we're just gonna define a new variable, which is eta. Okay. And now we're gonna see, and we're gonna define eta in terms of the Mach we're flying at. So this way, it's much more compact. So eta is defined as specific span squared if Mach is lower than Mach linear, and let's put 8 over pi. So I did a little change here. I'm going to tell you in a moment what I did. Specific span, and I'm going to call this specific mean chord, right? Let's put it. It's not the mean aerodynamic chord. So where does this come from? Well, I did a little change here. You can check where this comes from. Here there was a S surface over reference area. So S surface is just let's see. It's just the span over times the mean chord, right? Yeah, that's right. The mean chord, I just made this variable up. It's just the chord of the tip, well, the semi-sum of the chord of the tip and the chord of the root. The chord of the tip, just recall that if this is the rocket, this is the chord of the tip, the root, of course. This is C root, sorry. C root and C tip is this. So the specific mean chord is just the same way I define the specific span. It's just the mean chord over the diameter. You can check this. I just made I got rid of the dimensional part of the equation, so it's nicer this way. We don't have any S surface over a reference area. So this is a much nicer way, I think, to present this equation. And it also affects, it also affects theta. I can see now. Yeah. Oh, sorry, this is over. When Mach is above Mach linear. So we can also put eta in the theta, so we don't have to define, you know, two thetas independently, because the only thing that changes when Mach is over Mach linear is this part. So this way it's a much more compact way to define it. So eta is this. We have, sorry, theta is this. And then we have the body term. Yeah, much nicer this way. All right, if you substitute, we only need phi prime here. So if you do the substitution here, what you will get is that the natural frequency is equal to this. So again, we have, this is the density of the air, this is the, let's say, the mean density of the rocket, as we defined before. And then we have 1 over the length of the rocket, interesting, the velocity at which it's flying, and then we have a term here. This comes from the phi prime, of course, this term. Okay, so it's a very interesting function. So the natural frequency is gonna increase linearly with the velocity, and it's also going to increase if we have a shorter rocket. And then we're going to see what happens inside here, because we have eta that is piecewise defined. So in the next video I'm going to discuss yeah, I'm going to, you know, put practical realistic numbers in these variables, and let's see if we can make some conclusions with this simplified version of the natural frequency. Again, this is only to see, you know, which are the main driving factors of the natural frequency. This can be numerically kind of distant to the reality. Again, a rocket isn't a second order system, it's non-linear system. So we again, I just want to emphasize this. This is a simplification of the simplification. Okay, so just keep in mind that. But still, the interest of this is to see. From here, we can see the driving factors of you know, what's gonna affect the main let's say the most important factors in the natural frequency or the damping ratio. So it's not going to be close, probably numerically, to the real natural frequency, although there isn't a natural frequency at all, because we don't have a second order system. But still, we can see that, well, it's going to be pretty close to linear to the velocity, and you can see this term here. 1 over the length. We're going to see in the next video how is this going to affect, and you know, I'm going to put 2 examples, the Stratus 3 and maybe Rexus. So you can see how this, yeah, to get a feel of the numbers and the shape of the function. And let's see if we can draw some conclusions.